Our next speaker is Vamsi. Vamsi is a PhD student at TU Berlin, and his research interests are in buffer management, data center performance, and reconfigurable networks. He's going to talk about buffer management in data center switches. I think Vamsi is going to use the podium. Yes. Please.
So, hi everyone. Thanks for attending the talk. I'm Vamsi Addanki. Today I will be presenting ABM, Active Buffer Management in Data Centers. This is a joint work with colleagues from Princeton, MIT, TU Berlin, and ETH Zurich. I assume everyone in the audience are familiar with these two famous networking keywords, active queue management and buffer management. But don't worry if you've never heard, I will give a brief background. Indeed, the answer to what is ABM lies within this slide. Let me put it into perspective. On one hand, we have active queue management that controls queuing delays. For instance, approaches such as ECN-based, like RED, trimming-based, like cut payload, delay variants like CODEL and PI. In essence, AQM aims at providing stable drain time. On the other hand, we have buffer management schemes that control the overall shared buffer occupancy. Dynamic thresholds is a classic example here. Buffer management schemes aim at providing better isolation. Overall, in this work, we argue that providing better burst absorption indeed requires both isolation and stable drain time, not just one of them. Within this space, we propose ABM that works along these two dimensions simultaneously. So, ABM is a novel buffer sharing scheme for data center switches. We emphasize that it's not an independent combination of both AQM and buffer management. Rather, intuitively, it can be visualized as AQM that depends on buffer management. We hence call it active buffer management. ABM provides isolation across traffic priorities. It bounds queue drain time, and finally improves burst absorption. Before going into further details, let me give you a brief background on buffer sharing first. Both buffer management and queue management calculate drop thresholds for queues. Buffer management calculates thresholds for queues across the entire device, where the thresholds are dependent on shared buffer occupancy. On the other hand, active queue management calculates thresholds for a single queue, where the thresholds are a function of queue statistics, like average queue length. Importantly, buffer management and queue management act independently. This results in a hierarchical admission control scheme, where upon a packet arrival, buffer management first takes a buffering decision and then passes it on to active queue management. Finally, a packet is enqueued or dropped. To be precise, buffer management first calculates a threshold and compares it against the corresponding queue length. Upon acceptance, AQM then calculates yet another threshold, which is compared to the corresponding queue length. Finally, a packet is enqueued or dropped. This hierarchical scheme has overall thresholds that can be expressed as the minimum over the thresholds calculated by both the schemes. Here, it is important to observe that the function minimum implies that either buffer management or queue management is acting over a queue, but not both at the same time. Suppose we have large buffers. There is always enough amount of remaining buffer that buffer management gets suppressed, and eventually AQM becomes more important in these scenarios. On the opposite spectrum, like shallow buffers, for example, in the data centers, there is so little buffer that AQM gets suppressed and buffer management becomes more important in these cases. We hence focus more on the drawbacks of the state-of-the-art buffer management scheme, that is dynamic thresholds, which is used by Broadcom and Tofino switches. It is a simple allocation scheme where the thresholds are a simple multiplication of a configurable parameter alpha times the remaining buffer space. Unfortunately, This allocation scheme has two important drawbacks, that is, priority inversion, or in other words, it has no isolation properties. And second, the allocation scheme is oblivious to buffer drain time. We skip the analytical details in this presentation and only visualize them here. In this example, we show two priorities. Priority 1, which is considered as low priority, shown in black, and priority 2, shown in red as high priority. A single high priority queue is using the buffer, and on the x-axis, we vary the number of low priority queues that are using the buffer. On the y-axis is the occupied buffer. We see that as the number of low priority queues increase in number, they tend to use more and more buffer, leaving very little remaining buffer for the high priority. This creates priority inversion problems, or in other words, it doesn't provide isolation guarantees. Second, dynamic thresholds is oblivious to buffer drain rate. Consider this simple example where there are two ports, port I1 where 3 queues are using the buffer, and port I2 where a single queue is using the buffer. We are mainly interested in these 2 queues that are configured with the same parameter settings. They receive the same buffer allocation, have the same queue length, but it's important to observe that both these 2 queues experience significantly different queuing delays. Since the bandwidth is being shared on port I1 and I2, it's a dedicated queue. Overall, we find in our analysis that buffer management can, in principle, offer isolation properties, but it is fundamentally oblivious to buffer drain time. On the other hand, AQM can indeed offer stable drain time, but it is fundamentally, it cannot fundamentally satisfy isolation properties. Our goals in this work are both isolation and drain time, but as well as burst absorption. Our analysis also shows that burst absorption is indeed a function of both isolation and drain time properties. So what we are looking for is a region where we combine both buffer management and queue management that work simultaneously. This is where we propose active buffer management. ABM calculates thresholds based on an alpha parameter that is set for each priority in the traffic groups, also based on the number of congested queues of each priority that are using the buffer, the total remaining buffer space, and including the normalized dequeue rate, or in other words, how fast the queue is draining out. This whole allocation scheme can be intuitively seen as a block of buffer management and a block of AQM that are working simultaneously. Interestingly here, the buffer management part is a simple modified dynamic threshold scheme where we add this additional factor of 1 by n, which provides us isolation properties. The AQM part is similar to, for example, Pi or Codel, which use a specific set value where we control delay. And this provides us with stable or bounded buffer drain time. ABM has some interesting theoretical properties. First, it upper bounds the amount of buffer that is allocated for each traffic priority. Here, the bound is only based on the parameters that we set and independent of the buffer state. Second, it also lower bounds the amount of buffer that is available to a single priority. And this is important since now we can guarantee a certain minimum buffer that is available for each priority. ABM also upper bounds the buffer drain time, and this indeed offers us bounded queuing delays. All these guarantees are simply dependent on the configuration and the parameters that we set, and absolutely independent about the state of the buffer. More details about our analysis can be found in our paper. Finally, we evaluate ABM using NS3 simulations. We use a leaf-spine topology with 4:1 oversubscription. All the switches in our topology are similar to Broadcom Trident 2 switches. We use web search flow size distribution, and we superimpose it with a synthetic incast workload to emphasize more on the burst absorption. First, here we show the 99 percentile flow completion time slowdown for short flows. On the x-axis is the network load. We compare DT dynamic thresholds, FAB, which is flow-aware buffer management scheme, CS, that is complete sharing without any buffer management or queue management. IB here is the intelligent buffer that comes from Cisco, and we compare all these baselines to ABM. We observe specifically as the load increases, ABM can improve flow completion times by up to 76%. Even at 20% or even low loads, ABM is still able to offer improvement or similar performance compared to existing approaches. When we look at incast flow performance, ABM offers significant benefits compared to alternative approaches. We see as much as 80% improvement as the load increases. We compare ABM using more advanced congestion control and even more shallow buffers. Here, we use DC-TCP as the transport protocol. And on the x-axis, we show a spectrum of data center switches from left to right, reducing in average buffer per port per Gbps. On the y-axis is the 99 percentile flow completion time slowdown specifically for incast flows. What we see here is that ABM is able to sustain performance even until Tofino with such a small buffer, whereas alternative schemes like DT and IP, they shoot up in their performance as the buffer size reduces. With more advanced congestion control, alternative approaches are able to sustain performance, but eventually shoot up in their performance with Tomahawk and Tofino, for example, here. ABM is able to sustain performance across the entire spectrum of switches that exist here so far. Finally, in conclusion, we argued that existing approach of a hierarchical admission control scheme that simply combines buffer management and queue management independently is not enough, and it's fundamentally limited to a single dimension. We show that ABM offers isolation properties, bounded drain time, and then improves burst absorption. Our evaluation shows that ABM improves the performance of incast flows, and it also works well in shallow buffers. All our artifacts can be found in our GitHub repository. Please check it out. Thank you, and I'm happy to take any questions.
Yeah. Hi, Vamsi. Thanks for the great talk. Very interesting. I have one question. So you evaluated this in data center settings. Can you maybe say a bit what you would expect if you change the setting a bit? Maybe you add some optical circuit switch like in some of the other papers in this session, or you go into a wide area setting. What would you do?
So about the second part, in wide area setting, I think it really depends on whether the buffer size is large enough that buffer management becomes important, or AQM becomes more important here. So it depends. For example, if we deploy shallow buffers in wide area, then ABM can, of course, become a potential deployment case there. In reconfigurable networks, specifically, as far as I know, the model of buffer and what they require is significantly different. It's a virtual output queued model. Here we consider output queued switches. It remains future research direction to see how it works there. Thanks for the great question.
Yeah, great. Thank you.
Thank you for your talk. Great work. You showed that on the evaluation, the FCT actually drops on your, but what is the penalty on higher priority when you're comparing that to the traditional way? Meaning if you have higher priority traffic, like 60% or 70% of the traffic in a single moment is higher priority, what is the impact then when you have lower priority coming in on the flow completion time of the higher priority traffic?
So here, as long as we have high priority, we always give benefit to the high priority just because by definition we want to prioritize this traffic in the buffer. But the penalty on the low priority really depends on the configuration, and indeed it's possible to derive what penalty low priority would face, or it's hard to say in terms of flow completion times, but we have some results in the theoretical results in the paper that say how much minimum buffer that the lowest priority queue will get, even in the presence of all priorities that are using the buffer. So how to convert this minimum buffer that is available to flow completion time is a hard question.
Thank you.
Thanks for your talk, and I have a question about the queuing in your ABM, and how did you consider the arrival rate of packets in your system? Did you consider such a concept in ABM?
If I understand correctly, the question is, what is the arrival rate?
Yes, what's the arrival rate? And is there any assumption on the arrival rate in ABM?
So this is regarding the evaluation setup, right?
Mm-hmm, yeah.
So we consider Poisson arrival of flows, and the loads are across 20 to 80%. And then we also use the incast workload, where the arrival is also again Poisson with a certain request rate, which we mentioned in the paper. I think it's 1 request per second rate, still with Poisson arrival. This is like a distributed file system. There is a request, and then n number of senders start to transmit short flows.
Yeah. Okay, thanks for your answer. Thank you.
Thank you.
Any other question?
All right, let's thank Vamsi one more time.
Thank you.